In this video, we will be going over some antiderivative / integral basics. And without further ado, we start here with this particular exercise. We want to set up and evaluate a definite integral to find the shaded region. Now the shaded region is this here with these little slashes running through it. And it occurs to me that I do not have a function here. This function that is graphed here is y equals cosine of x plus 2. So the first thing we need to do in order to find the area of the shaded region is to find out the interval on which this area is existing. So it looks like x is going to go from 0 to pi, and that's going to be the first thing we need to write for our definite integral, from 0 to pi. And this is the function here. So we can say from 0 to pi, the definite integral from 0 to pi of cosine of x plus 2 dx. And so from here we can just follow the rules of antidifferentiation and get that the antiderivative of cosine x plus 2 is sine of x plus 2x, and we're evaluating that from 0 to pi. So what this means now is that we're going to take the pi value and substitute it in for the x's, and we're going to get something that looks like this. Let's do this. There we go. This will be sine of pi plus 2 times pi. And from that, we are going to subtract whatever we get when we take 0 and substitute it in for these x's, which would be sine of 0 plus 2 times 0. So then as quickly as I can get through this, sine of pi is 0 plus 2 pi. So this whole set of parentheses here reduces to 2 pi minus, here we have sine of 0, that's 0, plus 0, that's 0. So 2 pi minus 0 is 2 pi. This is our exact area represented by this shaded region here. For this next example, this is what we would call an initial value problem. We're trying to find the original function, and the original function would be f of x with no plus c values. We're looking for the actual constants here. And so we're given some hints as to how we can do that. We know f of x contains the point 2, 9. So how we can write that out would be f of 2 equals 9. And then we have this second bit of information here, has a horizontal tangent line there. That's at this point right there. So what that means when we're looking at tangent lines, the slopes of tangent lines, remember that's the derivative. And if the derivative has a horizontal, rather, if the original function has a horizontal tangent line, that means we have a slope of 0 at that particular point, but the x value is still needed. So we have f prime of 2 equals 0. And now that we have this information, we can go back and start finding the antiderivative of our function here, our second derivative, and work our way backward to the first, the original function f of x. So the first thing we need to do is we need to find the integral of the second derivative, and this is the indefinite integral, no limits here. Oops. No limits here, there we go. And so this would be 6 times x squared over 2 plus c. So what happens here is we can simplify the 6 over 2 to be 3x squared plus c. Now this represents the first derivative. and we can use this information here. If we substitute 2 in for x, we should get back, rather that whole expression should equal 0. So this should look something like this. If we substitute 2 in for x plus c, we should have this expression equal 0, which allows us to solve for c. And if you solve for c very quickly, you get that c equals negative 12. So this first derivative here is really f prime of x equals 3x squared minus 12. All right, we actually have to go back and substitute that minus 12 back in for c so we can get this first derivative here. And then we just repeat the process. We find the antiderivative of f prime of x. So we can find the antiderivative of 3x squared minus 12 dx. Again, indefinite, no limits of integration here. So this ends up being x cubed minus 12x plus c. And again, this is our function. So with our function here, I know if I substitute 2 in for x, I should get back 9. So this gives me an equation that looks like this. 2 cubed minus 12 times 2 plus c equals 9. And if you substitute, or rather if you solve for c here, this is minus 24, this is plus 8, this whole thing should be minus 16, add 16 to both sides, you should get c equal to 25, which gives us the equation then x cubed minus 12x plus 25. Just like we did with the first derivative, we have to take that c value and substitute it back in here, and that's where we get this plus 25. So here's our function. F of x equals x cubed minus 12x plus 25. In this example, we are doing something very similar to the last example on just the slide prior, and I'm actually going to just reveal some steps every few seconds or so. So you're more than welcome to pause the video at this point to try this. This just has a trig function instead of a regular old polynomial. So go ahead and give it a try. Like I say, I will release some steps here in a few seconds. And here is the final function. Now it's weird here, c is a couple terms big, negative 1 minus 3 pi. So we just tack that in for c like we do right here, negative 1 minus 3 pi. And I guess the only other thing that I could say here is that negative cosine of 0 is negative 1. And so when you add 1 to both sides, that's how this 2 becomes a 3. All right, next slide. For this example, we will be sketching the area given by this definite integral, and then we will use geometry to find the area. As of right now, normally in a Cal 1 class, you don't have the tools yet to be able to integrate this. So what you need to recognize is that this is a semicircle. And the center is at 0, 0. And it has a radius, the square root of this number here. So this is 16, square root of 16 is 4. So this has a radius 4. And so it looks something like this. There we go. And we're trying to find this area. So there's what the picture looks like. If you're just trying to find the area of this, we can find the area of a circle with radius 4 by using this formula. Area of a circle is pi r squared. So the area of this circle is pi times 4 squared, which is really just 16 pi. But this is for the full circle. We need to take half of this because we're looking at a semicircle. So the area here is 8 pi. For this last slide on this video, we are given some information here that the integral from 0 to 3, we'll say the definite integral from 0 to 3 of f of x is 4, the definite integral from 3 to 6 of f of x is negative 1, and then the definite integral from 3 to 6 of g of x is negative 5. So these numbers here, they just represent some areas, and we're just going to be adding and subtracting or multiplying some areas together to see what we get. And these are what we would say we're going to use the properties of definite integrals. So when we work through this first example here, we want to evaluate the definite integral from 0 to 6 of f of x dx. We can break this integral, this interval 0 to 6 apart as long as we have the same matching number, plus 6 f of x dx. And we can do that by looking up here. If we take the integral from 0 to something, well, of f of x, it looks like maybe we should stop at 3, because that is something we know. We know the integral from 0 to 3. We know the integral from 3 to 6. So we can break this interval down into two intervals, 0 to 3 and 3 to 6, and we can add these two values together. So I know that this first one is just, 4, plus this one here is negative 1. Our answer for the first one is 3. For the next one, it looks like we have an f of x and a g of x. So if I wanted to parse this out exactly right, I would say the integral from 3 to 6 of f of x, because this is exactly what we know. We don't know what the integral of 4 f of x is up here, but we can use the constant multiple rule to factor out the 4 to the front of this definite integral. So this 4 we can boot to the front. Then we can use the sum and difference rule here. We can subtract the integral from 3 to 6 of g of x dx. And this 3 here can also be booted out front as it gets factored out. So we know what this is. The integral from 3 to 6 of f of x is a value of negative 1. So this would be 4 times negative 1. So let's write that. 4 times negative 1 minus, again, that comes from this minus in the original integral over here, that minus. Let's see, we will have 3 times, what is the value of the integral from 3 to 6 of g of x? Well, that's minus 5. So let's say times negative 5. And if you simplify all of this down, you should get 11. Now for this last one, it's very similar to like this one here. We want the integral from 6 to 3 of negative 10 times f of x. Well, this is weird. We know the integral from 3 to 6, but not 6 to 3. So how we can get our limits of integration in the correct order is if we take the opposite of that integral. So switching these limits of integration puts this negative in front. The negative is still on the 10. Now we can bring this negative 10 out. We can factor it out, and it'll be a negative 1 times a negative 10 will give us a positive 10. Integral from 3 to 6 of f of x dx. And the integral from 3 to 6 of f of x dx is equal to negative 1. So we have 10 times negative 1 is negative 10. And then I have a little bonus question down here. So let's say I give you an extra piece of information. Here, the integral from 0 to 6 of g of x dx is 15. And I ask you to find the integral from 0 to 3 of g of x dx. Well, this is going to be very similar to what we did in the very first example here. However, we don't know these. We know these. So we'll actually have to solve for some sort of integral here. So here's what the equation would look like. If we're going from 0 to 6, we can break it apart at 3, very similarly to what we did up here. And we know this value, because we were just given that, that's 15. And we know this value, that's way back up here. So this equation becomes the following. We have 15 equals the integral from 0 to 3 minus 5. And so it looks like this, if we just add 5 to both sides, this should be 20. That way, if this were 20, and we take away 5, we end up with the 15 that we were given.